good?
I think they only get control of that. Like, oh, as soon as I doubted it, I guess it's.
That's what. Whatever works. Hey, great. Thank you very much.
No problem. Anything else?
Oh, we're good.
Good to go?
We're good. Thank you.
All right. I'll be up there if anything comes up.
Appreciate it. Think it's safe for me to start? Oh, it's streaming. Okay. Okay, welcome back, everybody. Thanks for your patience. Lots of logistics in the first few days. Okay, so we're going to start in on some more of the core material this time. I told you we're going to talk about a handful of different big topics in the class. We want to embrace dynamics and nonlinear dynamics. And that means some really specific things. There's a lot to know sort of in the world of dynamical systems. And we'll talk about a few of them, the ones that I think will serve us best to talk about, whether robots fall down or not in weeks forward. Yeah, so today I'm going to try to, how many people know who Steve Strogatz is? Anybody know Steve Strogatz? Steve Strogatz teaches a beautiful set of classes at Cornell about nonlinear dynamics. I think I've got his book here to advertise nonlinear dynamics and chaos. And Steve in particular has a very graphical way of helping to explain dynamical systems, which I think gets on the board very well. So I'm going to try to channel Steve today and give you some of the core concepts you need for understanding dynamics. Now, this is relevant for robots. It's relevant for learning theory. It's relevant for a lot of things. The way people optimize the performance of a gradient descent algorithm is actually very similar to the tools we're going to talk about today. And I'll try to make a few connections if people are interested in that when that comes up. But certainly, if we want to talk about the long-term behavior of a complicated robotic system, then we're going to need dynamics. Turns out we don't need super complicated dynamics in order to get the core ideas. We can do it in just one or two variables, typically. So I'm going to start with the simplest possible robot, which is our simple pendulum. Which, oops, got a bent pendulum. Simple means I'm going to assume the mass is at a point. I'm going to give it a length L, gravity, okay. And I'll call this angle, from vertical here, I'll call that angle theta. And it turns out actually that all of our robots are just a bunch of connected, almost all of our robots are a bunch of connected pendulum. Walking systems in particular, like I said, the double pendulum we looked at last time is almost exactly one of the simplest walking models. Okay, so even though this is painfully simple in some ways, it's actually very relevant. So if you want to generate the equations of motion for this, you might just know the equations of motion for this, but if you want to generate them, we could use all the same machinery. You shouldn't be afraid to use that machinery. If I wanted to write the kinetic energy, again, you don't have to because the software will do it, but it's so easy in this case, that I can just say that the kinetic energy is going to be, its mass times velocity is going to be length times theta dot. So, it's going to be 1/2 ml squared theta dot squared. It's my 1/2 mv squared for the pendulum. I have to pick a coordinate system for the potential energy. I'll just call it 0 at the origin. So with my theta like this, it'll get a negative mgl cosine theta. Okay, when theta is 0, I've got my energy is down here is negative. My potential energy is negative. If you then turn the crank of Lagrangian mechanics, you get out ml squared theta double dot plus sine theta equals, this is the terms for my Lagrangian, equals some generalized force Q, okay? So the generalized force in this system is going to be the torque applied around that joint. And we're going to model two types of forces there. I'm going to model the simplest model of friction. I'll just put a linear damping for friction at the joint. And then I'll assume I have a motor that could apply additional torque. Okay? So I'll say that Q is going to be negative B theta dot, because it's going to resist. If theta dot is positive, it's going to do work to resist that theta dot. Okay, and then I'll just call it my control input U. So these equations that we'll play with a bunch, I find even more complicated algorithms and the like. Sometimes I go back and say, well, how does it work for the pendulum? So you'll see these equations a bunch, and you'll become comfortable with them, but they look like this. I just move the damping onto the other side, but it really, in the Lagrangian sense, it really comes in as a generalized force. Okay, so, oh, by the way, this is also just a simple form of what we talked about last time, right? You can agree that this fits in this form. That's just a very simple version of it. The B you could put in here, but this is coming from, this is, I guess, in here. That's the gravitational potential, yeah. And then B is just 1, okay, but it all fits. Okay, so this is about as simple of a system as I can possibly give you. It's a differential equation, right? I have given theta dot and theta and U. I can tell you what theta double dot is, right? So it's, like we said, this is our theta dot is just some function of theta dot and U. So once you have a differential equation, then you should be able to do differential equation things, right? You should be able to say, for instance, if I give you theta 0, theta dot 0, then you tell me what is theta as a function of time. If I give you the initial conditions, and then I ask you where is the pendulum at time 42, you should be able to tell me that. But I've got bad news. I don't know how to solve that differential equation. It looks so benign. It looks so similar to the things you've seen in your differential equations class, but that sign is a nonlinear equation. And there are not, so even in the simplest case of no damping, you get elliptic integrals of the first kind. Once you put in the damping, you get nothing, actually, basically. Okay, so you can put this in a simulator, numerically approximate this, and take a numerical solution to that equation. That's certainly possible. We do that all the time. But if you want a closed form expression for this, you'll be sad. It doesn't work very well. Okay, now if I can't do it for this, I certainly can't do it for Atlas, right, for the back flipping humanoid. Okay, so we're going to need another approach that's not just straight up solving differential equations. So what are we going to do? And just to make that super clear, if this sign was not here, if it was a linear differential equation, then we do know how to solve it, and we've got good tools from that, right? So if I had, in the simplest form, if I had Q dot is just some A of Q, then you remember the solutions. Q of T is what is Q0 e to the AT. His solutions is that take the exponential forms, right? This is great. And actually, when you extend this to matrix linear equations, then you have matrix exponentials, and it's all beautiful and good. And as a consequence, we know a lot more about linear control than we do about nonlinear control. Okay, but that little benign looking sign, screws everything up. Okay, and most of our interesting robots have nonlinearities. But it also makes them really interesting, right? It makes them do beautiful things, and that's what today's about, is to think a little bit more about all the nonlinear versions of the dynamics. Okay, so if I can't answer that question, I have to think of a different question that I can actually possibly answer. So we have to change our mindset a little bit. There's still questions that you can answer completely precisely, analytically, okay? It's just not, the question of where is it at time t is a hard question to answer. If you ask it, where is it going to be at time infinity, that's an easier question, okay? Or if it starts at some place, will it ever visit some other place? I can answer that kind of question. Time makes it bad, but there's other quantities that we can say precisely, okay? And we're going to reframe our language to talk about that. We're going to talk about stability, reachability, concepts like this, okay? Now, so let's just connect really quickly to learning, okay? So I said one of the things that makes making hard in general is having to make long-term decisions, having long-term consequences of your action. So the control theorists and dynamical systems people have thought about that for a long time, and their answer to that is that you have to think about the long-term behavior, the stability. You can talk about limits as time goes to infinity actually easier than you can handle the details of how you get there. Okay, so we're going to start building that machinery. So that's the wrong question. Good questions are, let me say, limit as t goes to infinity of theta of t. That's a good question. Other questions, will I ever enter a failure state is another good question. Will my robot fall down? Turns out to be an easier question than where is Atlas going to be at time 42. Okay? Now we're going to have computational machinery to answer that question. We'll have math machinery to answer that question. But today we're going to do pictures to answer that question, because actually you get a lot of intuition from that. So today is graphical analysis. And this really is the Steve Strogatz inspired thing. Okay, so let's start doing graphical analysis. I think maybe I'll just stay here. Those boards are so dirty, right? I mean, I just worry that you guys want, this one's better than that one, but I still think it's kind of hard to see that, right? Okay, I'll stay here unless I really want to point at multiple things. And the trick was that they had the projector down here. So this board will always be clean for us, I think. That's a good reason to switch projectors. Okay, so graphical analysis is this beautiful thing. It's the simplest case of graphical analysis if you have a differential equation in just one variable. It can be arbitrarily nonlinear, but we want it to be in one variable. And this is a second order equation, so I need two variables to talk about it. So I'm going to simplify even the simplest system once a little bit in order to draw the first pictures, and then we'll get back to the full second order system. So, and this is also my excuse for teaching some of the beauty of dynamics. Okay, some of the best results from walking robots, for instance, actually came from theoretical physicists or theoretical mechanics people that came in and had very beautiful things to say about the way systems walk, right? And they are very careful and thoughtful about the way they simplify systems, and there's some lessons there, right? So if I want to make a one variable, first order approximation of this system, there's a regime dynamically where that's a totally reasonable thing to do. And that regime is when it's heavily damped, right? If I were to have a pendulum and I were to put it in molasses, okay, then it loses its oscillatory second order behavior, and it can, in a very high damping regime, will just look like a first order system, becomes simpler. So this is the damping here. And I want to consider the case where this b theta dot term dominates the ml squared theta double dot term. Okay, so now it's tempting to say, okay, well, what if just b is a lot bigger than ml squared? And that's not terrible, but it's not quite, they're not the same units, and you don't even know, like, am I going to experience very high velocities but very low accelerations? Something you have to do a little bit more to be. Okay, so what's the units of these things? So the units of this equation is torque. Okay, the units of this equation is torque, Newton meters, which is kilograms meters per second squared, right? Then that should check. This is kilograms meters squared, and this is 1 over second squared, right? But this term here is kilogram meters squared, and this term here is kind of a weird kilograms meters squared per second. That's what the damping units are. So if I want to compare a damping coefficient with a mass and length squared term, I need to somehow do, this is the dimensional analysis. You want to make sure they're in the same units. So I'm missing a factor of 1 over s in that comparison. So I need a characteristic time constant of my pendulum in order to compare those two. I want to say, on average, the behaviors I care about are the ones that are operating at this sort of time scale. And the natural time scale is the natural frequency of the pendulum. Okay, so if you get square root of g over L is the natural frequency, it has units 1 over s. Okay, so that's all to say that I don't want to write b is greater than ml squared. That sort of doesn't parse because it's the wrong units. But I'm perfectly happy writing b is square root of L over g greater than ml squared. It's the heavily damped regime. Now, we're not going to do lots of dimensional analysis in the class, but there's something so beautiful kind of happens in that, of you're somehow, I'm going to summarize all the things that this robot can do by saying I'm going to examine some characteristic behaviors of the system, and suddenly you get a beautiful sort of very simple concept out. You know, we talk about representation learning and machine learning. We talk about all kinds of interesting, powerful tools, but sometimes they're not as powerful as even the simple simple ideas. Okay, so in this regime, I'm going to say that this term dominates this term, and I'm willing to then approximate my system as just b theta dot equals u minus mgl sine theta. Okay. Maybe I'll keep it as approximate just to remember, but we're going to use that as our model for a minute. Now, there's even one extra detail that I'll get rid of, which is that so theta wraps around, right? And let's just ignore the fact that wraps around. So let me even just think about what it would be if it was mgl sine theta sine x. Okay, I've done nothing except change the symbol, but I want to just say that, you know, x is any real number, and this I don't want to have to restrict myself to anything that's wrapping around. Okay, so I'm going to draw this dynamics now. By making a plot, x versus x dot, okay? And it basically just looks like, I'll even say when u equals 0 for my first version here, it just looks like a sine wave. It's negative and it's scaled by MGL, but it looks like a sine wave, right? And those should be the same place, okay? This is MGL, negative MGL, right? Turns out just drawing that function tells me a lot about the more interesting questions about what happens in the limit as time goes to infinity. Okay, and so let's just think about that. So if I think about this plot, there's a few places of interest immediately. So there's 0 crossings of that function. What does it mean if that function is crossing 0? That means for some x, x dot is 0. Okay, so these are the fixed points of the system, they're called. So if I start at that point, I'll stay at that point for all time. Okay? But it's actually even more interesting than that, okay? In these first order systems, if my function could be complicated, it could be arbitrarily nonlinear, okay? But if it's above the line, if x dot is positive, then I can think about it as a system who's flowing that way. And everywhere it's below the line, I can think about it as a system that's flowing this way. You get me? Okay, so no matter how complicated my function was, I can say instantly that as time goes to infinity, any initial conditions that started here are going to end up at that fixed point. And I'm going to call this a stable fixed point. I'm going to color it in the Strogatz way, okay? Because what do I mean by stability? If I start away from it, I'm going to return to it. We're going to be very precise about the word stability in a second, but just for now, if I started near it, I'm going to converge back to it. Okay, so does this make sense intuitively? Right, so what are the fixed points of the overdamped pendulum? There's one at 0. There's another one at pi. There's another one at 2 pi. There's another one at 3 pi. Okay, those are the, right? Okay, and these are stable, and these are unstable, right? So they're right there. Now, but I could, like I said, I could have put aerodynamics in here if I wanted to, right? And it would have been okay. I would have still had a great answer. It's sort of interesting to think what does u do if I were to just put a constant torque in? Now, what would it do to that function? Just move it, the whole thing up and down, right? So what does it do to the fixed points? Yeah, so right, so as this is moving up, the fixed points are going to go here, but this one's coming this way, so the fixed points actually come closer together, which is interesting, right? So if I apply a torque at my shoulder there, then I got my fixed point here moves this way, but I also have a fixed point here that's moving this way because I have a torque resisting that gravity. Okay, what happens if u exceeds MGL? Yeah, I did that once in lecture. I brought a real hardware pendulum down, and I was like, what happened? I said almost exactly that. I was like, what happens if you set u greater than MGL? And then I did it, but I thought I had a current limit. And the pendulum went across the room. Did that just happen? Yeah, so now I do software demos. Yeah, but that's true, right? So those fixed points converge, and once this thing is above the line, all the way above the line, then all trajectories just go that way until the wires come out of the electrical socket. That's what saved me that day. Okay, but it turns out we can say most of so we got this fixed point, we got the notion of a stable fixed point, but there's even more words that you should know here. If I look at the set of states right, that are in here. It's just on the line, of course, but it's between those fixed points, right? All of the initial conditions, not including that point, between here and here, will converge to that point. They might go slowly at first, but then they'll converge. So that area, this is the region of attraction. Of that fixed point, also called basin of attraction. And if you want to be fancy, the manifold that separates the basins of attraction is called the separatrix. They can do funny things in higher dimensions. Here they're nice and simple. Okay, so every stable fixed point will have a region of attraction. Questions about that? Yeah.
If you set U to be precisely MGL, what would you call the
Okay, good.
that sort of
Yeah, so we're going to talk about that. So I went from U strictly less to U strictly greater than. So if you have these kissing, just barely touching right here, right? So they're going to be marginally stable fixed points, right? They'd be stable from one direction, but unstable in the other direction. But even that, you need a bigger vocabulary in nonlinear because of the ways they can be marginally stable. So let's do that. Let's talk a little bit about the different ways you could talk about stability. So a linear system is either stable or it's not. Or marginally stable, or it's either stable, marginally stable, or unstable. And a linear system will only be stable at the origin. That's all it can do. Okay, you can think about that. If I had a q dot equals aq, a could be 0, it could be negative, or it could be positive, but they're all lines going through the origin. Okay. Nonlinear systems can do all kinds of crazy things, like we just heard about, they could make glancing contact with the line and do interesting things. So we have to be a little bit more careful about definitions of stability. And we'll start with notions of local stability. Right, we're going to talk about, and we already used that. So when I said that fixed point was stable, it's only locally stable or regionally stable. It's not globally stable. Okay, there are different words we can put to use if we want to talk about, do all initial conditions converge to a point? That would be a globally stable system. Okay, but we're going to talk about a more local sense. So in what sense is a fixed point of a nonlinear system locally stable? There's a few definitions that you should have in your toolkit. You can be locally stable in the sense of Lyapunov. Cool kids call that ISL. You can be locally attractive. You can be asymptotically stable, locally asymptotically stable. Or you can be exponentially stable. And there's more too, but these are the ones that will change the programs that we write a few weeks from now when we're writing code to define stability. Okay. So intuitively, the notion of being stable in the sense of Lyapunov says if I start near the region, I won't go too far away from the region. Attractive says, I'm going to write these carefully in a second. Attractive says, I will actually get to the region. This one just says, I don't leave a ball around the region. This one says, I'll actually converge to the region. If you're both attractive and ISL, then you're asymptotically stable. That says for initial conditions, as x goes to infinity, I'm going to get there. I'll write this carefully. And then exponentially stable actually says a little bit more. It says there's some rate at which I get there. I'm going to get there faster than a linear system with a particular constant. Okay? So you can see maybe how different systems will have different properties. In fact, the undamped pendulum, if I took an undamped pendulum and I put it near the bottom, okay, I started it near the bottom, it will never converge if it's undamped, right? It'll just sit there oscillating forever. So it's not asymptotically stable, it's not attractive, but it is stable in the sense of Lyapunov, okay? And then you can have things that converge but not at an exponential rate, right? I think the glancing collisions would have some quirkiness because their derivative goes to 0, right? So, okay. Now the definitions, I don't want to spend too much board time on the definitions that are all there, but let me just sort of give you the basic, they're all in the notes written carefully, but I'll give you the basic gist here, right, of what this kind of looks like. So I said this is, if you start near the fixed point, you'll stay near the fixed point. So how do you make a formal statement about that? Okay, you say, for every epsilon, where epsilon, so I'm going to use epsilon and delta are small numbers. Okay, for every epsilon, there exists a delta. This is there exists a delta such that if my initial condition is within a delta ball, this is a useful exercise here, it's within a delta ball of the fixed point. This is x at time 0. Then that implies that for all t, x of t minus x star is less than epsilon. And we're going to have, there's a problem on the p set to help you think through that carefully. So what does this notation mean? So think about these as balls. So this is if I took the Euclidean norm here, just the squared norm, so it's just Euclidean distance between x and x star in my state space. Okay, for that to be less than some constant, that's just a ball in state space. Okay, it says for every ball in state space, I can find some smaller ball, which must be strictly contained, because if this is true for all t, then for it to be true for 0, delta must be smaller than epsilon. Sorry if I said that fast. You find me an epsilon ball. If I tell you, prove this epsilon ball, you have to be able to tell me a delta ball that's inside it, such that trajectories that start here, they might walk around, but they'll never leave the epsilon ball. That sounds totally weird. Why would you have two balls, and maybe why would it ever leave one ball and go in the other ball? But it's completely practical, because oftentimes, like the local stability guarantees will be not circular, for instance. But if you say the delta ball looks like this, then you can say something about it'll never leave the epsilon ball, which is big. Okay, so that's why we have that extra machinery, is because the local invariant sets, we'll talk about all these things, the local invariant sets may not be circular, but that extra gap gives you the power to work with local dynamics that are not contained by the Euclidean norm. Okay, so that's the type of machinery we're going to use. We're going to say there's a distance. You start some distance from the fixed point, just like I did there. I started some distance from the fixed point, okay? And this doesn't say that I'm ever going to get there. It just says I'll never go too far. Okay, attractive says that limit as time goes to infinity, x of t goes to x star. Okay. This is, and asymptotically stable is ISL plus attractive. The one I think the one we picked on the problem set was there's an interesting case of how you can be attractive. I'm sorry for the word, that's not my word. You can be attractive but not ISL, which is kind of a weird thing. But there's a couple of good examples. We put one on the P set. Okay, and then exponentially stable, like I said, is that it says that I'm going to get closer, that I can even bound the distance here between the fixed point is going to be less than some exponential. So there's a linear system that this sort of corresponds to, and this is going to converge faster than the linear system. The fact that we needed, so linear systems are always exponentially stable if they're stable, and that the exponential stability does imply the others. Okay, but the fact that we have to get into this extra stuff is just a foreshadowing how interesting nonlinear systems can be. They can do all kinds of crazy things. They can change the number of fixed points as you change parameters. The fixed points will come together, or they'll explode apart. There's all kinds of it. You can have multiple fixed points, of course. We already saw that. You can have limit cycles. You can have manifolds that are all stable. Right? This is the wild world of nonlinearity with a neuroscientist. Do you believe that? A computational neuroscientist. I was building robots down the hall where they kept the monkeys. That's where I could get my milling machine and stuff like that. Okay, so but my advisor was a fantastic computational neuroscientist, and he studied the dynamics of neural networks, because that's what I can draw on the board. But the ideas scale. Okay, the pictures don't scale, but the ideas scale. Okay, so neural network. Even a recurrent neural network. That makes it dynamic, right? Okay, if you think about the standard equations of a neural net, I've got weights coming in from some input. I'm going to put it through some nonlinearity. I'll use a sort of a tangent nonlinearity, okay? Typically this would be something like tangent of, these are weights W, weights, and I'll call my inputs U. You know, that would be a standard sort of neural network. Recurrent neural network has to do a little bit more. I'm going to loop in the simplest case, I'm going to take the same neuron, I'm going to loop its output right back into its input. Okay? This is kind of a bizarre thing. Okay, I've still got my tangent nonlinearity. In order to have that be not just an algebraic loop or something that makes sense, I have to now talk about the dynamics of how the activation changes inside the neuron. So the standard model here would be something like x dot equals negative x plus tangent of wx. If I go to vector form. This is actually, this one neuron self-looping network is known as an AUTAPS. I don't think we know yet, or we certainly didn't know when I was a grad student, whether we find them in the brain, but you do find them in a dish. It happens sort of often, I guess, when you culture neurons in a dish, and they're now lonely, and they start growing back their connections, their processes, and they start making connections, then they start connecting to themselves because they got nothing else to connect to. So you get these neurons that start getting excited and stimulating themselves and the like, okay? And it looks like this, right? So this is just one neuron that's been isolated. You put in a dish, and it's growing its dendritic processes out, and it starts connecting to itself. Okay, and it's a fascinating system because it's, you can see it's one of the simple illustrations of short-term memory, right? That somehow something as simple as that, as simple as this, could tell us a little bit about memory, and we can understand it with graphical analysis. Okay, so let's graph this function, shall we? What does a tanh look like, right? I've already been cartooning it here. Tanh of wx is, if I draw it a little bigger, you know, it goes from -1 to 1. This is tanh of wx. Okay. If I do, what does -x look like? That looks like this, right? That's -x. So if I put them together, then what happens is I get the tanh sloped by the -x, right? So I get, the picture looks like x dot. I got my line of slope 1, and then I have one that's offset by 1 in each direction. And the tanh makes it so that the equations look like this. This is x dot equals -x plus tanh of, let me just say x. So I should say w equals 1. If I change w, I can make this steeper or less steep. Okay, that's what w does. It changes the gain of that, which is interesting, right? As you can see already. So what are the implications now for stability? I'm not going to ask you what x is at time 42, but what is x at time infinity? It's 2 fixed points if I have enough w's, right? I've got 2 fixed points here. Which one's stable? Oh, sorry, I got 3 fixed points. I missed the in the middle. Which ones are stable? Which ones are unstable? Two outside are stable, yeah. Okay. Right, these are going to go. I go like this, like this, like this, like this. And that's an unstable fixed point in the middle. Okay, so this is the simple analogy of short-term memory is I have a latching mechanism, in some sense, that has 2 fixed points. Okay, and if I play with this, okay, so if I change w, I get my curves like this. Does that show up well enough? It's kind of a little faint, but okay. So this is as I change w, I get a sharper or more flat curve. Okay. What happens if I add in a u? If I do wx plus u here, I can actually shift that whole thing around. Okay. So u in this case, kind of like in the pendulum, but I can move it around with activation coming in. Okay, so if I'm down here, then I have a fixed point at around -1. Okay. If I'm up here, I've got a fixed point at +1. And if I'm here, then I've got 2 fixed points, 2 stable fixed points, right? The interesting thing is now if we think about this as memory is that I can sort of, because it's bistable in this off configuration, you can sort of turn it on and latch it at one side, or turn it back off and latch it at the other side, right? So if I were to just, for instance, put a square wave in so that no matter where it starts, if I pull it down enough, I know it's going to be on that side, and then I bring it back to 0, it'll still be at that side, right? Because you've got an initial condition. Let me say that again. So if I pull it down this way, then I know and I wait long enough, it'll converge towards this fixed point. Now if I bring it back up, the state was already here, so it's going to stay at that fixed point. Okay, if I were to bring it far enough that way, it'll jump to this fixed point. And even when I bring it back, turn off my activation, it will remember that it was on that side. Okay, so this is just putting a little impulse in. So so it started at 0, U started at 0, so it went to the positive fixed point at around 1, and then you kick it, and it goes to the other fixed point around -1, but then when you turn it off, it remembered that you kicked it, right? So one neuron, but it has an interpretation, if you like, as memory. Now, it turns out this is not that far from what people use in recurrent neural networks. Like the LSTM unit has lots of inputs, lots of outputs, has some state, but the long short-term memory, LSTM, long short-term memory, so this is short-term memory, the one I had on the board, long short-term memory. Not my favorite name, is the sort of standard winning unit until transformers came and killed it, maybe, but the standard unit you'd use in a recurrent neural network, right? And it's basically the taps with more inputs and more outputs, and it has one extra big, well, okay, the LSTM model has, it looks like the Swedish chef just kind of threw nonlinear functions into the pot. In my mind, but there's some people who have gone and said, okay, well, actually, what do you need for the LSTM to work? You really just need this Janet model is like a very simple version of the LSTM, and it's basically exactly what we had in the taps, but it has one extra thing, which is a forgetting gate. Okay, so I have the tanh, and I have this one extra term, which is an extra input, which allows you to just say, neuron, forget, okay? And if I plot that, we can understand what that does here too. Not that one. Okay, so same thing, I could put it in a regime where it looks a lot like the taps, okay? But if I were to take this forgetting input, UF, I can just it's like, I don't know, hitting it with a electromagnetic pulse or something, forget everything, and then it goes back and you can be a normal neuron again, okay? And this is what's actually used in recurrent neural networks, yeah?
In the autopsy equations, where is U?
Oh, good, I didn't write it, but I said it. So if I were to make it have U, I put it right here. We could put a W on front of it too, but that's where I put it, just to have a scalar U come in. Yes?
Does this have any applications in like physical or mechanical systems?
So it's interesting because, so my advisor, who is a theoretical physics guy that turned into computational neuroscience guy, he always talked about neurons as circuits, right? So people, and you think about bistability as a transistor, right? Or I think that all these things have direct analogs to analog electronics, for sure. Okay, there's one other, yeah.
In the example you just showed for making it forget, once you go back to this normal state, it's going to be at an unstable fixed point. Does that mean anything? Does that for the network? Or?
Right, it means, so in this particular, the set of motions I just went through would have it, so it would, when it goes to being zeroed, it would start converging back towards the origin, and then whichever side it happened to be on, right, it would then go this way. Does that make sense for a neuron? I would say that LSTMs work better than I think they should. Or I should say, I don't understand why they work. They seem kind of crazy to me. A transformer, by the way, which is the thing that's been replacing recurrent networks in a lot of applications, can also be, I can't draw it on the board because they tend to be very high dimensional, okay, but it also has a perfectly good dynamical system interpretation, if you do the causal version of a transform. Good. So questions? Yeah.
So U is 0, it's only remembering the positive.
So in the LSTM, there's two versions of there's two U's. There's the forgetting one. So let me set U forget to 0, and then when U is 0 in the model I've got, often they would put a bias in, for instance, too, which would change this answer a little bit. But right now, when U is 0, there's two fixed points. It could be on either. You have to turn U high to go to one side, and it'll remember that you went high, or you turn it to low, and it'll remember you went low when you go back to 0. Yeah? Make sense? There's a lot more, here. So, like I said, the way people analyze even learning rates of gradient descent algorithms. If you wanted acceleration-based algorithm or whatever, then they're using tools from dynamical systems theory to talk about rates of convergence, for instance. Okay, if you want to talk about even just convergence, there are inequalities that come from dynamical systems theory that talk about whether these things converge at all. One of the cool new themes that you might have heard is that now we don't just talk about convergence to a fixed point. When you're talking about optimization in a neural network, for instance, one of the themes would be that all minima are global minima. So then you get these weird fixed points that are all equally good. Okay? Just throwing breadcrumbs if you think about that kind of stuff. Oh yeah, there's one other idea that's super cool about memory. It's an old idea, I guess, if you will, about memory and recurrent neural networks. Who knows what a Hopfield network is? It's like lost in time. It was such a good idea, but it's not like implemented in PyTorch. I bet it is implemented in PyTorch, but there's this great idea of that a recurrent neural network can store memories. The simple case, it had one idea, one memory. Okay, but in general, you could say, I have multiple fixed points, right? Like my pendulum had multiple fixed points. Maybe I could say this one is associated with one memory, this one's associated with another memory. Okay, so there's a very simple recipe, actually, for programming a recurrent network to have fixed points exactly where you want. And it's called a Hopfield network, okay? So this was Hopfield's model of associative memory. He'd say, I want to remember these 3 images. He would construct, not necessarily with learning, he would just set the weights of the neural network, in the simple case, such that the fixed points are the images, and the region of attraction was that if you're close in some pixel space, you will actually converge back to those images. Such a good idea, right? Dynamics fill in the details. And it turns out it's a very simple construction where you can write the weights of the neural network so that there are fixed points exactly at some capacity. There's interesting questions about how many neurons do you have, how much capacity do you have, how many images can you remember. But there's a very simple recipe for just setting the weights of a neural network so that it has fixed points at your images. Awesome, right? Good, yeah.
I've been thinking about neural networks as function approximators.
Okay.
Not something that necessarily not as a dynamical system. Could you bridge these two?
Good, thank you for asking that. So yeah, actually, so John Hopfield is a theoretical physicist. There was a bunch of work in computational neural networks before that were done by theoretical physicists, okay? And actually, I heard an interview, a podcast or something not so long ago from John Hopfield after deep learning happened. And he says, and I totally believe it, he says the things that we're still missing is we're thinking about learning too much like a function approximator, and we don't think about the dynamics of learning, right? There's information comes in some flow, right? Memory happens in some flow. Time matters in the way our brain processes information, right? And he thinks we're missing that. Now we use recurrent neural networks, which are dynamical systems today, as you, for instance, crawl along a sentence. The simplest, maybe traditional application would be in a natural language processing. Let's say you want to translate machine translation. You want to translate from English to French or something like this. You would run a neural network and just enter as an input on each time step one character or one word, and you just walk along the sentence, and you'd have another part of the neural network kicking out the other sentence. Okay, it's a little more complicated than that, but that's the bit. So that's an example of sequence to sequence using neural networks as a recurrent neural network, which is as a dynamical system. That doesn't have a beautiful flow of information in the same way, but it has a sense that the state of the current thing is something about the state of the sentence. What do I have to remember about the sentence? And interestingly, what broke down with those when transformers came in was that at some point you couldn't make super long sentences with recurrent networks. They had a limited capacity for memory. They didn't scale well. The more neurons you added didn't give you like arbitrarily more sentence capacity. So transformers have come in, and they're a slightly different representation, and now you can have ChatGPT write you an essay, right? But that started in the recurrent network kind of space. Sorry if that's a tangent.
Like if it's not a recurrent neural network, does it also have dynamics, or is it only recurrent networks that have dynamics?
I think the recurrent networks have dynamics. So the feature of the dynamics is that you somehow the state evolves in time, right? So you need some mechanism for that to evolve in time. If it's really just y as a function of x, then I don't think dynamics gives you much about describing those systems. Okay, so I promised we'd do second order systems. We've done only first order systems right now. Second order systems are still amenable to graphical analysis. They're just a little bit harder to draw. And you've probably drawn phase portraits of systems before, and that's the stuff of graphical analysis for second order systems. Okay, so let's go back to our full Okay, so again, I said when we're going to write second order systems as in our x dot equals f of x form, we have to make a decision of sort of what is x. If you're a physicist, you might use position and momentum. But in robotics, we use position and velocity. Okay? So we're going to choose x. In this case, would be theta and theta dot. Always, in this class, we'll always say that the way you convert a second order system into a first order system is writing two equations, right? So the x dot then is just theta dot, and then I have whatever, 1 over ml squared times u minus b theta dot minus mgl sine theta. Right, so these are two first order systems. When solved, help me understand the second order system. So the way we're going to plot that now is we're still going to plot, we now have to plot theta and theta dot. And what I want to plot is, you see, this is now, it's a vector differential equation, right? I've got a state vector in, and I'm going to get a derivative vector out, just two-dimensional vector. So the elements of this are a vector. So if I want to plot what the dynamics look like in this space, it's going to look like a vector, right? It's going to look like where the x component is theta dot, and the y component is theta double dot. Is that clear? So if I draw a bunch of vectors around here, I can sort of map out what the dynamics are going to do. Okay, and if I were to follow that vector, it turns out if I were to, if I were to actually, at any given point, the dynamics, if I were to start at some initial condition, it'll actually follow those vectors along. That's the interpretation of that vector in the two-dimensional plot. Okay, so what I want to do is start plotting those vectors. And I'll do it for the case now of b equals 0, and I'll do u equals 0 first. And it turns out it's sort of easy to do when theta dot is 0. It doesn't even matter. But when theta dot is 0, u is 0, I just have negative mgl sine theta divided by this, so I just get g over l sine theta. And it looks like, and this component is 0, so it looks like this. It's 0 here. I get a little vector pointing down here. And then the magnitude of that vector in the y-axis is the sine. Okay, the magnitude of the vector here. Okay, it's going to look like this. Is that kind of clear? The theta dot, double dot term, when those are 0, is just a sine. And if I were to plot it along the theta dot axis, then the x component is just theta dot, so it's going to go like this. And if theta is 0, this term is 0, it's just that. So it's going to be this, which grows just linearly with theta dot. Yeah? Okay. So if I start following, well, first of all, I can already identify that there's fixed points here. Any point that's a point, this, when theta dot is equal to 0, those are my fixed points. I can see them still. But what's much more interesting is when I start following the flows. Oh, sorry, yeah.
Sorry, I'm trying to understand still this drawing.
Yes, please.
I would expect there to be a y component in those horizontal lines since there's also a theta dot term.
You're completely right, but when b is 0, it's flat. Yep. I will draw the damped version in a minute. Yep. Completely right. Okay, so, but you can kind of see the pattern, right? Trajectories are going to go around like this. Okay, and that's actually always true. Whenever your theta dot is positive, you got to be going that direction, right? Yeah. So it turns out if I were to follow this, it does things like this. Try to plot those. Okay. But it gets more interesting when I get in the vicinity of these fixed points here. It kind of elongates like this. And you get this weird Eye of Sauron thing happening. Okay. And then if I were to do it over here, there's another eyeball over here. Okay, and over here, you get this other eyeball over here. And interestingly, if you start up here, it goes like this. And down here, it goes like this. Okay, so let's just make sure we understand those bits, right? So first of all, this is a fixed point. We already talked about it's stable in the sense of Lyapunov, but it's not asymptotically stable. And you can see right here, trajectories here could stay in the vicinity of it, even in a ball that's about the right shape, okay, but it never converge for the undamped pendulum. And these, as I get here, I'm getting bigger and bigger oscillations. The undamped pendulum will just go around forever, okay? If I get myself on this particular orbit, right, this one here, this This is called the homoclinic orbit. It's closer to what you were thinking about before, Tommy, right? But the homoclinic orbit is a particular one. If I have, if I'm in the homoclinic orbit, I will go like this. And then if I was just a little, if I would just go and come to rest. If I were just a little bit off, I might go like this, or I might go like this. Right? That's the homoclinic orbit as I'm approaching that. I kiss the fixed point. Yeah. These are actually, in the undamped pendulum, these are orbits are defined as levels of constant energy. If I wanted to plot those curves, those are the constant energy curves because there's no damping. In this particular system, it has the mechanical interpretation of that. So this is exactly the energy of the upward fixed point, which I know to be MGL, because it's MGL cos negative, MGL cos theta up there, and the velocity is 0. So I could say that that arc is the energy equals MGL arc. Okay, and it goes right here. If I start it with more energy than that, then what happens? Right? And if you start it with way too much, then you have a bad demo. Good. Now, if I were to add damping back in, right, if I add b equals 0, then I add a component in that direction, okay, to all of these vectors. And suddenly now, you won't be surprised, but it'll start spiraling back in, right? This one changes the vector field and becomes asymptotically stable to the origin. And these are always unstable fixed points. But then you get all kinds of wonderful things like I could start out here and I could go bump, bump, and then get trapped in this one, for instance, right? If you lose energy, you go around twice, then the last time you don't make it and you're trapped, right? So the basin of attraction of this fixed, let's say this fixed point, not only, it looks like this weird, beautiful thing that kind of has this tendrils out here, right? These are all the states that could possibly land and get caught in that fixed point. And then it actually has the mirror image down here, right? These strange bands of initial conditions, which if you play it out, land in that fixed point. And if you remember that they're the same fixed point, then it's, you could talk about it differently. But is that kind of clear? So it's a little harder to just say I can plot any curve and visually tell you what type of stability it is, but you can still learn a lot by plotting these phase portraits. And we're going to plot on top of this the result of solving for value functions and other things like this. And the physics of the problem will be revealed by the optimal control algorithms. Right? So sometimes I will occasionally have this experience where I'm talking to a reinforcement learning person and they're showing me some plots and I'm like, your plots are flipped, right? And they're like, what are you talking about? You don't know what code I wrote. Or, well, no, your plot's flipped, right? It's like, because it'll be like elongated in the wrong direction. And I just know, because I've drawn a lot of phase portraits, that you can't have a value function that looks like that for a mechanical system, right? And so it really does connect to the modern algorithms. Okay, one last point to make. I don't want to jam too much down your throats here, but that's a lot of cool dynamics, I guess. But what we're going to do in the class is control, right? So our goal should be to change the vector field. So that's when u stops being 0. And when I was doing it graphically, I was just saying u is a constant. But it's much more interesting if u is a function, right? It could be a function of state, for instance. So what do you get to do with u, right? You don't actually get to change the x component of the system. So you're going to go that direction whether you like it or not. You get to change is you get to add something in that direction. If you're torque limited, maybe you'd only get to add a little bit. You get to change the vectors a little bit, right? If you're underactuated, maybe there's some directions where you can't change it at all and other directions where you can. Okay? You could, if you're fully actuated, you could erase the board and say, I want this vector field, and you impose it. As long as it's a vector field of a second order system, that could work. But that's not the game we want to play. What I want you to play is think about what's the minimal change in that vector field that shapes the dynamics and kind of reflows the dynamics to the place you want, right? I don't know, like Mickey Mouse in Fantasia or something like this. Just kind of, try to send my, I want to get to that fixed point. Let's just kind of change the vector field a little. Let physics do most of the work. Okay, so what we're going to be looking for is algorithms that will allow us to think about that, right? The long-term consequences. A small change here could play out with me eventually tipping up and ending over there. But I have to work through the dynamics to understand that. Okay, and the tools we're going to use are optimization and machine learning. Any questions about that? Cool. Yeah. I will see you next time. The problem set is posted on Piazza. If you haven't joined Piazza, please